All right, so let's get started. Before we start, we actually need to import the various libraries that we're going to use in this project. All right, so this is going to be a bit lengthy, more than the other project that we're dealing with. All right, more than the other projects that we'll be doing. But stick with me. We're going to go through step by step together till we get to the end of this. All right, so let's get started. And before we start, as I said, we need to import the various libraries that we're going to need in this project. All right, so to save time, I've already imported these libraries in here. All right, so I have numpy as np, so that I will not be typing numpy over and over again. I'm just going to use np when I need numpy. All right, then also have pandas. I have matplotlib and seaborn, and I mean for visualizations I also have matplotlib inline, so that I'll be able to plot these plots inside the Jupyter notebook. I have the other libraries also being imported here, and we're going to use them as at when they are being needed. All right, so let me collapse it so that we have space in moving forward. All right, so what we're going to do is to actually load our data set, all right, so that we can be able to work on. By the way, we can also use just the PyForest to get all these libraries being imported at once. So if I should just run this, you can just see that let me comment this one, and then if you do from PyForest importer start just like from PyForest import everything. All right, now if you run this and then you want to see the various libraries that automatically have been loaded or imported for you, use lazy underscore imports, and then you get everything. So if I run this, you can see that you have a lot of libraries which automatically have been loaded for you, so you don't actually need to be importing these one by one. All right, so let me comment it so that when you get the notebook you can actually do that by yourself. All right, so we're going to load our data set. All right, so I'm going to use pd dot read underscore csv because our data in our data set is actually a csv file. All right, and by the way, this data set is available on Cargo, and it's also available on UCI machine learning repository. You can easily get it. I will also load it on the platform for you, all right, so that you can easily download it from there. All right, so if we run this, it's being loaded and saved into this variable df. So let's see the head of it. All right, we use the dot head to see the head of it, and when we print that, this is the data set that we have, and this is what we're going to work on. All right, so here you can see that we have cement component 1 kg in a m cube mixture. We have blast furnace slag component 2 kg in the m cube mixture. We have fly ash component 3 blah blah blah. We have water, we have super plasticizer, we have coarse aggregate, we have fine aggregate, we have age, we have concrete compressive strength, and this is our target here, right? This is the strength, and this is, I mean, our target. This is what we are going to try to predict. All right, so this is our target, and if you look at the names of the columns, it looks quite heavy. It's too much, it's a lot, so I'm going to shorten these names. For instance, if you take cement component 1 kg in a m cube mixture, I'm just going to shorten everything here. I'm going to just get rid of this and then just name everything as cement. All right, so over here I'm just going to name everything as cement. The same way over here, blast furnace slag blah blah blah. I'm just going to shorten everything and just name it as slag. All right, and if you come here, instead of say fly ash component blah blah blah, I'm just going to shorten everything to ash. All right, the same thing over here. I'm going to shorten everything to water, and over here, I mean, let's do that so that we get to see it. So if we do this, this is just rename it. So I'm going to use df.rename, right? So I'm going to use the rename function over here, and then if you see it over here, let me go up a bit. Now you can see that we have cement component 1 kg in a m cube mixture. Right, the same thing I've picked here. Cement component 1 kg in m cube mixture. Right, I pick everything, then I rename it as cement. Right, the same thing. I pick blast furnace slag. All right, component 2 kg in m cube mixture. Then I name it as slag. All right, the same thing as fly ash, right? Fly ash component 3 kg in. So I copy everything from here, right? Then I put it here. I put everything here. Then I rename it as ash. Okay. The same way I copy water component 4 kg in a m cube mixture, right? Then I put it here. Water component component 4 kg in a keep mixture, then I name it as water. All right, so I do the same thing for all the other columns, right? I do the same thing for all the other columns. Now, after that, if we see the head of it again, just like we did to see this, right? So if we see it again, you see that now we have a very beautiful column names, which we can actually deal with as simple as that, right? So instead of cement component 1 kg in a keep mixture, I'm just calling it a cement. All right, and instead of say blast furnace slag component 2 kg in M cube mixture, I'm just calling it slag. All right, I'll do the same thing for all the other columns. For instance, our targets are like concrete compressive strength MPa megapascals. I just name it as strength. All right. So we can also check the data types that we have. All right. So as you can see, these are floats, float, and then we have integer here, and then we have float. So if it's decimal is float, right? Python recognizes as float, and if it's just a whole number like this, it's just recognized it as an integer. That's why we have float, and then integer for the age. All right. For the age column is an integer, and then the rest are floats. All right. We can also check how many rows and how many columns that we have in our data set by using just a df. And then if we do that, we see we have 1030 rows with 9 columns. All right, with 9 columns. Don't forget we just printed the head of this. So if I do this, you can see that we have all of them here. Although there will be a break here from 29, we have a break here, but we have 1030 rows by 9 columns here. All right, so let me collapse this a bit. Just printed the first 5 rows so that we have space over here. All right. Okay, we can also check if there are any null values in here. If there are any null values in here by using just the df dot is null, all right, dot sum. All right, if we do just df dot is null, we're going to have some true, and false. But it's going to be very difficult to spot the true. If there are any true in here, it's going to be very difficult to spot that true, right? I mean, false means that there are no null values in there, and if you see any true, then it means that there are some null values in here. All right, but don't forget when it moves to say 29, it breaks here, right? It breaks here and then goes all the way to 1000. All right, so if there are any null values in between here, we will not actually see. All right, so the best thing to do is to actually use the sum so that you can easily get every column and see that if there are any null values in there, it will calculate and then count how many null values that are present in that particular column. So in this particular data, we don't have any null values in here. If you see the cement, the number of null values in there are 0, slag 0, ash 0. The same thing for all the other columns, right? So we don't have null values in here. We're good to go. Now we can also check the shape here, right? We can also check the shape. I mean the describe to see the minimum, the maximum, the Q1, the Q2, the Q3. That's the first quarter, the second quarter, and the third quarter. All right. So by just using the describe function. So if you run this, now this is what we have here. All right. So we have the cement, the slag, the same thing, but we have the count of each. Each of them is having 1030, of course, as we checked above. And then we also have the mean for each. So the mean for cement is 281.16 or 17 if you want to run it. And the mean for slag is 73.24. And the mean for say ash is 54. I mean the same thing for all the other columns. And we can also see the standard deviation, the minimum, the 25th percentile, the 50th percentile, the 75th percentile, and then the maximum in each of these, right? So if you want to just make it easier to view, you can just transpose it by using the capital T. All right, and then over here you can see the count, the mean, the standard deviation, the minimum. Just changing the orientation of this table. All right, this matrix. All right, so you can see the cement, the slag, the ash are here, and then the count, the mean, the standard deviation comes here. It becomes more simple to actually visualize and understand it. So if you can see the strength of we can see that the maximum strength here is 82.6, whilst the minimum strength here is 2.33. All right, so you can just have an idea of in each column over here just using the describe function. All right. So we can start by doing some exploratory data analysis here, all right? So we're going to start with the cement, right, to explore and then see how these columns are being distributed, all right? So, and I mean, have an idea of what we are working with. So we're going to start by the cement, and this is what we're going to do. We use the describe to get this 25th, the 50th, the 75th percentile, right? We can also explicitly calculate all these, right, by just using this quantile function which is present in stats, right? So if you import stats, you can actually do that, right? Which is also in SciPy. All right. So for the Q1, we're saying that if you pick the cement from our DF, right, and then we calculate the Q1 from it, which is 25th percentile, and then for the Q3, which is the 75th percentile, right, which is this 75th percentile. So this is the Q1, this is the Q3, right? This is the Q2, which we're not calculating here, but we're calculating the Q1 and then the Q3. All right. So 25th percentile and then the 75th percentile. Then after that, we will print it as first quartile is Q1 and then the first third quartile is Q3. Then after that, we find the interquartile range by using this IQR function, which is present in stats in SciPy. All right, to find the interquartile range. So if we do that, now you can see that we have first quartile Q1 is, so first quartile Q1 is, so this is the first quartile that we have, right? So our Q1 for cement is 192.375. Let's verify to see if that is true. So if we go to cement, and then we see the 25th 192.375, right? So the same thing that we have in here, 192.375, and then if we see the Q3 for cement, we have 350.0. Let's verify and see 350.0 here. All right, so it's the same thing. Then we use the IQR to calculate the interquartile range. All right, so this one will help us to actually detect if there are any outliers in here, so which we are going to work on right now. All right, so let's set a limit. If anything is below some the lower limit, then we call it an outlier, and if there's anything which is above the upper limit that we will set, then we will call it an outlier. All right, so we're saying that for any 1.5 multiplied by the interquartile range, don't forget Q3 minus Q1 is just an the interquartile range, right? You can also use this function to calculate that, and alternatively you can just use Q3 minus Q1. All right, so anything which is, if you subtract 1.5 multiply by the interquartile range from the Q1, anything which will below that number, right, anything which will go below this number will be an outlier. And if you add 1.5 multiplied by interquartile range to the Q3, anything that will go beyond that will be an outlier. All right, so now if we run this, we will see that we have the lower limit that we set for the cement is negative 44.0625, and then the upper limit that we set for this is 586.4375. So any value in cement that will go below negative 44.0625 will be considered as an outlier, and anything that will go beyond or above, or any value which is in cement which is greater than 586.4375 will be considered as an outlier. All right. So doing so, we can actually set it over here and then say that anything which we can use this particular one here to detect. Right, here is just calculating the percentage. Let me separate it so that you can see it very well. Okay, now over here what we are doing, let me comment this. Actually, this is just putting it in the percentage form, so let me just comment it. All right, so now what we are doing here is that if you go into the DF, which is our data set that we've loaded, and then you pick the cement, any value in there which is greater than this, right, which is greater than the upper limit that we set, becomes an outlier. So we count how many that are there. All right, and then we go and then any value which are in the cement and is also lower than negative 44.0625, we actually count it as an outlier, right? So we count how many are there which are outliers. outliers. All right, so if we run this, now we can see that we have, this is the percentage part. We can see that we have 0, 0 in there, meaning that there are no outliers in there. There are no values which are less than this. There are no values which are greater than that. So there won't be any outliers in there. All right. Now we can verify this by using the box plot. Right. So if we plotted the box plot, you can see that the maximum is here, right? The maximum, this is the minimum, this is the maximum, this is the 25th, this is the 75th, right? And this is the 50th percentile. So Q1, Q3, and then Q2 is here. This is the maximum, this is the minimum, right? And then after the maximum, there are no values in there. After the minimum, there are no values in there. If there were to be some values in there, you would have seen some dots in here, or maybe some dots beyond here, all right? So in this case, this box plot actually confirms that there are no outliers in here. This just like we just find out over here. All right. All right. So we're going to do the same thing for all the other columns, right? So we can actually see the distribution of the other columns. I mean, just like we did for cement, we can also do the same thing and then see the distribution that we have for all the other columns. So as we did for cement, right, by trying to find if there are any outliers in there, we can do the same thing for all the other columns. So let's see if we can do the same thing for water. All right, so this maximum and minimum are the same thing that we did over here with the describe. So I'm going to skip that, and then I'll start by finding the Q1 and the Q3 for water. All right, so just like we did for cement over here, all right, just like we did for cement over here, finding the Q1 and then finding the Q3 for cement, we're going to do the same thing for water here. So we're saying that the Q1 for cement, right, we use the quantile, and then we see that the Q1 is obviously the 25th percentile, and then the Q3 is the 75th percentile. All right, so we do that, and then we print it out. All right, then we print it out from here. All right, so it's just the same thing here, W underscore Q1, the same thing I'm printing out here. All right, so I want to be able to print everything, that's why I'm just putting them here. All right, then after that, I also find the interquartile range by using the IQR function, which is present in stats. All right, so I'm going to use this IQR function to find the interquartile range of water, of the water column. Right, so if I do that, see that I have the first quartile, which is the Q1 of water, is 164.9, and then the Q3, which is the third quartile, is 192.0. All right, and it's the same thing that we have using the describe function. All right, for the water, you see that the Q1, which is this, is 164, and then the Q3 is 192. All right, over here, and then with the help of the IQR, we are able to calculate the interquartile range to be 27.09 or 27.1. All right, so we can also set the limit. All right, we can also set the limit that anything which will be below 1.5 times the interquartile range. This is the Q3 minus Q1. All right, Q3 minus Q1. Remember, W underscore Q3 is just Q3 for water. So we just put W there so that we will differentiate it from the Q1 and the Q3 that we did over here, right? So that we show that this Q3 is for water and this Q1 is for water, right? So this Q3 minus Q1 is just interquartile range, all right? It's just interquartile range over here. All right, it's just interquartile range over here. All right, so 1.5 times that, and then Q1 minus that. So anything that will go beyond this, all right, I mean below that, will be an outlier, and anything that will go above this will also be an outlier. All right, so anything that will go above 1.5 times the interquartile range plus the Q3 will be an outlier. All right, so if we do that, we see that, okay, the lower outlier limit that we set for water will be 125.25. So anything that will be less than 124.25 will be considered as an outlier. All right, and anything that will be greater than 232.65, right, if you want to run it, will be an outlier. So anything that is greater than this value here is an outlier. Anything that is less than this value here will be an outlier with respect to the water column. All right, so if we do that now, we can actually see how many outliers are present. All right, by this one is just the percentage as I did above over there. So let me comment it again here so that you just have a focus on this one. All right, so this is saying that if you go into the water column, right? If you go into the water column and then you find any value which is greater than 232.65, as we set over here, which will become the upper, right? Anything that is greater than that, right, is an outlier. So count that for us. And then we count how many that are existing. And then anything that is below 124.25, right, as we said over here, anything that is below that in the water column, we just find that, and then we count how many are there, and then see if there are any outliers there. All right, so if we run that, we see that there are 4 values which are greater than this. There are 4 values which are greater than 232.65, right? And there are 5 values which are lesser than 124.25. All right, so there are some values in there. There are some outliers in there. All right, so we can also use the box plot to actually verify this. Now, if you see that, you can see that at the upper, I mean, this is the maximum, right? This is the maximum here. This is the minimum here. So, and you can see there are still some points which are existing here. There are still some points, unlike the cement, right? There are no points after the maximum. There are no points here, so there are no outliers in there. But for this, there are some points in here which represent some outliers in here. All right, we can also do this plot for this water. All right, so let me just get rid of that and then run it again. Okay, now you can see the distribution for the water column, right? Almost a Gaussian, almost a normal distribution. All right, which is a good thing to work with. All right, we can do the same thing as we did for water, as we did for cement. We can do the same thing for slag. All right, we can do the same thing for any of the columns that we have. We can do this kind of analysis to see if there are any null values present in there. So let's try and then do the same thing for slag. This is the same thing that we got from the describe. So I'm going to comment that out. All right, I'm going to take it out to collapse that cell. All right, and then over here we can also do the Q1 and the Q3 for slag. All right, so we go into a DF and then we select slag, and then we calculate the 25th percentile and then the 75th percentile from there. All right, and then after that we can actually set the limit. All right, the outliers in there. So anything which is less than that, all right, 1.5 times the interquartile range, which is the Q3 minus Q1, and subtracting it from Q1. Anything that will go below this, any value that will be lesser than this, will be considered as an outlier. And any value that will go above 1.5 times the interquartile range plus the Q3 will be also considered as an outlier. All right, so if we run this, we have this. All right, so anything which is less than negative 214.42, all right, will be considered as an outlier, and anything which will go above 357.375 will be considered as an outlier. All right, now if we do that, right, this one is just the same thing that I showed you earlier on. So I'm going to comment this again. All right, now if you see this one here, all right, so we are saying that anything that is above this, any value that will be any value in the slag column which will be greater than 357.375 is considered as an outlier. So we go to the slag column and then we search any value which is greater than 357.375, and then we count how many are there. All right, the same way we go into the same column, and then we see that only any value which is less than negative 214.425, all right, any value which is less than this value, and then we count how many are there. All right, and if there are any, it becomes an outlier. All right, so if we do that, we see that we have 2 in the upper, right? At the upper level, there are some 2 values which are greater than this. There are some 2 values which are greater than 357.375. All right, so we have 2 values that are greater than that. We counted it and we got 2 values that are greater than that. All right, but when you go to the lower part, right, we don't have any values which are less than negative 214.425. All right, that's why we have 0 here. Okay, now we can verify this from the box plot, right? We can use the box plot to verify this. Now if we do this, you can see that on the upper, after the maximum, there are still some points there, but the minimum here, right, there are no other point there, right? There are no other point there. That's why the minimum is 0 here, but the maximum is having some two other points which are greater. All right. So that's it for the Slack. We can also do the same thing. For all the other columns, we can do the same thing, right? So for the age, so let's consider the same thing for age. All right. So we can start by calculating the Q1 and also the Q3 for the age. All right. So we calculate the Q1, which is the 25th, and then the 75th for Q3. All right, and then after that we can also set the limit that anything which is below this, which is Q1 minus 1.5 times Q3 minus Q1, and anything which is above Q3 plus 1.5 times Q3 minus Q1 is just the interquartile range. I hope now you know that. All right, so anything which is above this 1.5 times the interquartile range plus the Q3, anything above that in the age column will be considered as an outlier, and anything which is less than 1.5 times the interquartile range and subtracting it from the Q1 in the age column will be considered as an outlier. If we do this, we see that we have a negative 24.5. So saying that any value which is less than which will be less than negative 24.5 in the age column, right, will be considered as an outlier, and any value which will be greater than 59.5 will be considered as an outlier. All right. The normal circumstance is supposed to be an absolute value because we don't have negative ages. All right. So over here you can see that we put negative 24.5 here, that any value, right, in the age column, right? So we're saying that going into the age column, search all the values. If any value there is less than negative 24.5, then count how many are there, right? Then we will see how many outliers are in there. That's a threshold that we have set, that any value which will be less than negative 24.5 is an outlier, and any value which is in the age column which is greater than 59.5 will be considered as an outlier. So we count how many are there in the upper, how many values are greater than 59.5 and how many values are less than negative 24.5. Right. So if we do that, we can see that at the upper level we have 135 values which are greater than 59.5, right? But on the lower side we don't have any value which is less than negative 24.5. All right, we can confirm this with the box plot. All right, if we plot the box plot, we can see that there are a lot of values which are over here which are greater than this 59.5. All right, which are greater than 59.5, and all of those values have been considered as an outlier. All right, has been considered as an outlier. And to point it out, we can adjust this. Considering the fact that as much as 131 values will be considered as an outlier, we can increase our threshold, right, from this 59 to maybe a different value, so that we will limit the number of outliers that we will remove, right? And then, as I said, we can also do the same thing for all the other columns, right? So we can do the same thing for hash column. So this is the exploratory data analysis. This is the univariate data analysis that we're doing to get to know each of these columns that we are dealing with over here. All right. So if we do the same thing for hash column, we can see that we have any value which is less than negative 177.45 will be considered as an outlier, and any value which is greater than 295.75 will be considered as an outlier. Now if we do that and then we check these values which are greater than greater than this, let me bring this one here, which are greater than this, any values which are greater than this, and any values which are less than that. Alright, so I'm going to run this. So before I do that, let me run it from here because I did not run it earlier on. So I'm going to run it all the way from this part. Alright, I'm going to run it all the way from this part so that I'll override it. Alright. Okay. Now if I do this, and then let me comment this one out. and then I do that. So any value which is greater than 295.75 will be considered as an outlier, and any value which will be lesser than negative 177.45 will be considered as an outlier. All right. So now if I run this, we see that there are no outliers in there. Now let's see the box plot and see if there are any outliers in there. Now this one confirms that there are no outliers in there. All right. So now let's see a multivariate data analysis for all these columns that we've been dealing with. All right, so we can also do it for all the other columns that we have in our data set. All right, so we can end it here, but we can do it for all these. Right, you can do it for all these columns to see if there are any outliers in there. So I'm going to do a multivariate analysis over here to see how the distribution of each of these columns are. So we're going to do the same thing. We're going to set a figure size to, the 3 by 3, 3 rows and then 3 columns. Then I'll set the size to length of 16 and then width of 16. All right. And then our first plot for cement. Let me just run this so that you can actually see how it is when I'm explaining alongside. All right. So this 3 by 3 here is saying that you have three columns here, and then also we have 3 rows. All right, if I zoom up, 1, 2, and then 3. All right, and then we have 1, 2, 3 here. Right, that's what is happening. And then 16 by 16. Right, that's 16 length. All right, and then 16 width. Okay, 16 width. Okay, so the first one is just cement, right, which is this one. This is the distribution of the cement. It's the same thing that we did up here, if you remember, when we were doing the univariate data analysis. Let me go up. Okay, for the cement, we did not draw that for the cement. All right. Okay, this one is fine, but it's the same thing that we are getting over here. For instance, for the water, we drew it for the water. All right. So the same thing over here. Right, it's the same thing, the same distribution that we are getting over here. Okay, so we are plotting that one on the first position, which is 0 0. All right, so this is the first 0 0, 0 1, and then 0 2. Right, 2 1. 1 0, 1 1, and then 1 2. All right, the same thing that is these numbers that you can see here. Right, as 0 0, as 0 1, as 0 2. All right, so this is just showing the position where we are plotting these cement, slag, ash, and water superplastic coesque, and then fine air aggregate, age, strength, respectively. All right, so if you can see the distribution of all these attributes that we can see that we have some normal distribution, some are approximately normal distribution. All right, and some are also right skewed. Right, you can see some of them being right skewed. Right, so this gives you an idea of the distribution of those attributes that you're going to deal with. All right, so let's move on, and then see there are some observations here for you that you can easily read when you get to the notebook. All right, so we can also use the pair plot to see the correlation which is existing. All right, so if we run this pair plot, this is what you're going to get. We're going to have this distribution here, which is also showing you the correlation among each of these attributes. All right, so for cement and slag, all right, you can see it from half of it. Right, if let me see my pen. Okay, so now you can see that you can watch it from above, from either below or from above. So always the diagonals are going to be the same, but you can watch it either from this side, or from down here. All right, so that's basically what is showing over here. All right, so let me get rid of this. All right, now you can see that there's less correlation among these attributes. All right, so we will not face what is called the multicollinearity problem here. All right, we are safe to go. But if there was a strong correlation, then we might want to deal with that correlation before we move on to perform any machine learning or to build any model on this kind of data set, right? But in this case, we are okay. The correlation is very less, so we don't need to worry about collinearity or something like that. All right. So let's see the correlation. I mean, with this correlation, we see that there's very low correlation among these data sets. We can also use the heat map to get a better view of that. All right, so if we plotted the heat map, we can see that we have a very beautiful heat map here. And then diagonals are always going to be one because it's just, um, as I said, a correlation between itself. I mean, it's like cement and cement will always be one, slag and slag will always be one. It's just like cement, and then if you trace it down here, it's cement, right? So cement and cement, slag and slag, right? If you trace this one, slag here, all right? If you pick slag here, something like that. If you pick slag here, and then you trace it down, all right? If you go down, you're going to meet another slag over there. With my pen, I cannot scroll down, but let me get rid of this pen and then see what I can do. Okay, let me minimize the size. Instead of 35, I'm going to use, say, 20. I'm going to use, say, 20 and probably 10. All right, so let me run this again and see. Yeah, this is a bit simple and small for us, so I'm going to use my pen and get rid of this. Now what I was saying is that we can actually use slag, and then if we trace it down here, we can see that it's slag and slag, right? So it's always going to be one. All right, it's always going to be one, just like now if we pick, say, water, right? Water here, and then water here, right? It's always going to be one. So obviously the diagonals are always going to be one, right? So if you're reading something like this, you just consider either up here, right? You just consider either up here, or you consider the down part, right? It's always the same thing. So cement, and then slag. This is negative 0.28. This is over here is slag, right? If you trace it down, it's slag, right? So you just consider cement and slag is this. Cement and ash is this. Cement and water is this. All right, cement and superplastic is the next one. All right, so if we consider cement, if we consider say cement and say water, all right, you can see that we have 0.0013, which is very less positive in correlation. All right, almost all of them are very less, either very negative or very less positively correlated. All right, so we don't need to worry about correlation in our attributes. All right, so we don't actually need to worry about any correlation in these attributes. So moving on, we can actually get rid of this. So let me get rid of the pen. Okay, we can also use the box plot to actually spot the various outliers that are present in our data set. So all right, so if we plot the box plot, we can see that there are some outliers which are present. All right, there are some outliers which are present in there. All right, there are some outliers which are present in there. All right, so we can deal with this the outliers that are present with the help of this box plot. All right, now with this that we've written here, we are saying that any value, right? I'm using if you see over here, right, what is happening over here. Let me just bring my pen, then I'll just write it for you to see. All right, so I'm going to write this what is being coded here. I'm just going to write it in simple words for you to get to understand it. All right, so what is happening over here is that if you see this, right, df.cement is just the cement part. All right, and then df.cement.mean, so any value which is in the cement, right? So let's say any value which is x, right, in the cement. Let me off this. Any value which is in the cement, all right, minus the mean. That's what is happening here. Any value which is in the cement minus the mean, all right, divided by the standard deviation. So that's why df.cement.standard deviation here, right? And then after that, we'll check the condition. If it is greater than 3 standard deviation, all right, if it is greater than 3 standard deviation, we call it an outlier. All right, so it's just the same thing that we're dealing up there, just different way of arriving at the at the same thing. All right, just a different way of arriving at the same thing. So if you see this one over here, to just any value in the slag minus the mean of the values in the slag divided by the standard deviation of the values in the slag. All right, we want the absolute value because we don't want to consider negative. So if we get, say, negative 14.2, we find the absolute value of that, all right, so that it becomes 14.2. All right, so that we get rid of the negatives. Right, that's why we have the ABS, which is the absolute value of that, and anything which is greater than the standard 3 standard deviation of that, we will consider it as an outlier. All right, that's what is happening over here. All right, so let me get rid of this. So if we do that for all the columns, for cement, for slag, for ash, for water, for superplastic, for coarse aggregate, for fine aggregate, for H, this is what we have. We can see that slag is having about four outliers in there. Water is having about 2 of them. Superplastic is having about 10 of them, and then we can see H is having about 33 of them. And that is what is showing here. H is having more of them. Strength, superplastic, water, and then slag. All right, that is what is showing over here. That is what is showing over here. All right, don't forget we are checking the greater than. That's why this one is showing those that are above. All right, it's not showing those that are below. All right. Okay, so now we can replace these outliers with the median of each of the columns. Right, we can do that and then replace each of these outliers with the median of the column. All right, so what we are doing over here is actually going to replace each of these outliers. Right, remember we use this function to calculate the outlier. So that's just anything that is below this, right, it will be considered as an outlier, and anything that is above this will be considered as an outlier. All right, so this is just calculating the Q1, and then which is the 25th percentile, and then the Q3, which is also the 75th percentile, and then finding the IQR, which is the interquartile range, and anything which is below this will be considered as outlier, anything above this will be considered as an outlier. So what is happening over here is that we are saying that if you locate any value, all right, which is lower than what we've described here, all right, or any value which is higher than what we have described here, all right, we replace it with, right, we replace it with the median of that column. Right, remember we are saying that course, right, course, we find course in the df dot columns here, right, with exception of the strength. That's why we're counting from the back, saying the negative 1. All right, if you're a bit familiar with NumPy, you know how we can also do negative counting, negative indexing, right, counting from the back, all right, which starts from negative 1. So we are taking everything with the exception of the strength, which is at the last position. All right, then after that we will check the box plot again. Now you can see, if we compare the two box plots, you can see that there was a lot of outliers in here, but after that there's a bit lesser, even with the H, which is having most of them has been reduced. All right, most of them has been reduced, and even the others are not even having it. All right, so we are a bit okay. So we will do the feature engineering in the next video. All right, so from here we are a bit okay with the data pre-processing and the exploratory data analysis. So in the next video we will start with the feature engineering and model building. All right.